All right, welcome back. We are ready for lessons 73 and 74. No, I will not jump out and scare you or attempt to, although the bell may scare you. I got some flack from that one with the coronavirus get up. Again, you saw my disclaimer. I do think it's wise to abide by the authorities' suggestions and laws, which I wasn't trying to poke fun and say we shouldn't stay 6 feet away and all that. Anyway, that's in the past. We'll never hear about that again, hopefully. I think I might delete that video. Lesson 73. This is now more trigonometry. So we talked about sine, cosine, and tangent. Oscar has a hold on Arthur, that kind of thing. We're starting to actually apply them now. How does it work in real life? I'm going to put this up here for reference. The sine, Oscar, well, that's up on the H. Oscar has a hold on Arthur. Sine, cosine, tangent. Oscar has a hold on Arthur, just to make sure we have it there, because we will use it today. A couple things to look at. Angle of elevation is an angle formed by a horizontal line and a line of sight to a point above. So two terms, angle of elevation, angle of depression. If I'm standing here and I'm looking straight out and I see something out there, and then I see a bird in the sky and I lift my eyes, that is, I elevate my eyes up. What is that angle? What angle of elevation to where I'm going for? And then the same thing, if the bird decides to look at me, he's flying along up here and he sees somebody down here, so if he depresses his eyes, he lowers his eyes. So what is the angle of depression? Now I'll just say it up front. You can see by the diagram, both references, so here's the bird, and he's looking this way, horizontally, and here's a person down here on the ground, and he's looking this way. These are parallel lines. They're reference lines, but they're both perfectly horizontal. So the angle of depression of the bird to see me is exactly the same as my angle of elevation, because this is parallel to this. Here's an angle and here's an angle. They are alternate interior angles, transversals and so on, parallel lines. So the angle of depression is this one. Angle of depression, and the angle of elevation is this one. Angle of elevation is this one. Same reference, and it really doesn't matter if you're trying to solve and say, well, what is the height above me, just directly the height above me of the bird, and I'd be concerned about this. I could also come over here and do it here. So my triangle on the bottom, I'd be looking at this one. The bird, if he's trying to figure this out, he'd be looking at this one. Well, these two triangles are congruent. This is congruent to this, so it doesn't matter if you use the angle of depression, doesn't matter if you use the angle of elevation, just use the right triangle when you're looking at sine, cosine, tangent, and which one are you talking about. And we'll get more into that. But angle of depression is going down, angle of elevation is going up, they're congruent to each other. You can use trigonometry to find the angle of elevation and the angle of depression and the lengths related to it. So here's the first one, example 1, using the angle of elevation, and this child is flying a kite. And they have an 80-foot string. They know that because they measured it or whatever. They know they have an 80-foot string, and then they measured that 36-degree angle, and they'd like to know if the kite would drop straight down, how far would they have to walk to get the kite, I guess you could say that. Since we're at 36, when we're dealing with a hypotenuse and we're dealing with an adjacent, then we are going to do this. Adjacent and hypotenuse, so we're dealing with the cosine, which they tell us that. So the cosine of 36 degrees is adjacent over hypotenuse. Cosine of 36 degrees is adjacent over hypotenuse. Adjacent, we don't know what it is. Hypotenuse is 80. So the cos of 36 degrees is some number over 80. And then put that in your calculator and solve it. Cosine of 36 and x over 80, solve for x, and you get x is 64 feet. We've done this before, it's just now applying it actually to a problem. Top of the next page tells us what we were just talking about here. That is alternate interior angles, and they're congruent. So angle of depression, angle of elevation, they are congruent. All right, going to the next one, example 2. This is a plane now, pilot in a plane cruising at 33,000 feet. That's 33,000 feet above the ground. He sees a lake out ahead. The angle of depression to look at that lake is 30 degrees. He has to lower his eyes 30 degrees, and then he sees the lake. And the question is, how far is the plane from the lake? And that is that slant distance. So the hypotenuse is what they're concerned about, not necessarily the distance over the ground. But, I mean, either one you could use. It's just going to determine which function. If you're concerned about, let's say this is a plane and here's the lake now, and you know this is 33,000 feet, we're just adapting this drawing, 33,000 feet, then if you want to know this length or if you want to know this length, you could figure both. It would just tell you, it just determine which one you're using. Or if you don't like that, since we're using angle depression, you could think about this upside down triangle up here, and over here is the 33,000 is this. And so you could decide, you know, just the straight line distance till he's directly over it, or if he'd fly straight into the lake, how far would he go until he gets there? So the problem is concerned about this one, which is the hypotenuse. And you're given a 33,000, which is the opposite. So opposite over hypotenuse, that's the sine. The sine of a 30-degree angle, opposite over hypotenuse. And you should be able to recognize a 30, 60, 90 triangle in here. If this is 30, which we said it was, 30 degrees, then this is 60 down here, and this is 90, of course. This is 33,000. That is half of this one. If you lay this triangle up, like we usually do, and do it like this, and then we're concerned about this length right here. We said this is 33,000 feet. It's going to be exactly half of this, so 66,000 feet for that one. And then you can also find that. That is 30, 60, 90. You can use 30, 60, 90 if it happens to be a 30 degree. If it doesn't happen to be 33 degree, then, or 30 degree, then you use these, or use them anyway. Angle of elevation from multiple points. Example 3, this is just like two problems in one. A window washer is working 60 feet above the ground. He's up on top. I never made sense of that, how exactly he's washing there, but maybe he's on a platform. That's point C. And then his direct height above the building is 60 feet. The question is, how far away is each person pictured at street level, and that is X and Y. Again, the distance, the hypotenuse distance. And so you have to do them use two different problems, but for both cases, the unknown length is the hypotenuse, and you're dealing with the side opposite. So opposite over hypotenuse, you're going to use the sine for both of those, for both problems, for both x and y. So the sine of angle A, that is the furthest out one, the sine of 40 degrees is 60 over x. Put that in your calculator, you get x equals 93.34 feet. And then the length of BC, that is length y, the sine of that is, that's a 70 degree, so the sine of 70 is 60 over y, and then you get 63 feet. So it makes sense. Person B is a little bit closer, because it's a little closer to direct up and down, which would be 60 feet if he were directly underneath of him. But he's a little bit out, so that's 63 feet. The other guy's further away, gets longer, 93 feet. Example 4 quickly. This is bottom of page 485. Surveyor on the credit union building. So he's on top of the left building. It says credit union if you can read that. Surveyor on the credit union building measures an angle of elevation of 15 degrees to the top of the adjacent building, the business park, which is a little bit taller. So he's on top looking out, and oh, there's a taller building. He's got to go 15 degrees up to see the top of that building. And they know that the credit union building is 600 feet tall, and they know that the business park building is 800 feet tall. The question is, what is the horizontal distance, that x value? And it's a little tricky the way they give it, but your triangle that you're dealing with is on top there. So you have, in other words, your reference point, I draw it out here. Here's the buildings, and your angle, you're setting here, the angle's there. This is 600, this is 800. It's like your reference is 800, so you simply take 800 minus 600, and that tells you this is 200 feet. This building is 200 feet taller. That's really what you want to know. This is 15 degrees. You need to know this because you're dealing with this triangle, and the question is, what is this? So you're looking at opposite and adjacent. So that looks like the tangent function to me. Tangent function of 15 degrees. That's the 15 degrees. So the tangent of 15 degrees is opposite over adjacent, and opposite is 200. So 200 over x, and you're trying to find this. Tangent of 50 is equals 200 over x. Solve for x and you get 746 feet. Seems like the bell is really ringing this morning. I'm looking for one thing. I found it. Turn the page to 486. If we would be together in class, we would have made some of these hypsometers, but we're not in class. This is using a protractor and turning it into a tool to measure angled elevation. And you can see how they did it. Take a weight, it's a little cumbersome, but take a weight, a string and a weight, and tie it right on 0, and that's hanging down. That's just your gravity point. And so as you tilt this up, your string is straight like this. You can see it. And then you measure, and you're trying to find that angle. It makes sense in the book, actually, easier. Tape a straw on the edge so that's your sighting thing. You sight up this line, and then you have to hold that and read this. There are better ways to do it. Here's one way. This little thing. It's a tool with the shop. We don't use it much, but can you read that? So if I tilt it up, it tells you the degrees, and I get it up to about 45. So I could tape a straw on this, and then just sit here and do this. But again, I'd have to have somebody reading it or hold it perfectly still. And then what is that angle? If you're just measuring an angle from a level to here, because I put it on level. See how level we are? That says it's 0.6 of a degree on level. There's 0 and 0. So that board needs to go like this, according to this thing. It's like a level. Works upside down. If you flip it upside down, then the numbers change. It's kind of cool. You go to there, and they change it back around that way. That's one way, but this is pretty low tech as well. You could probably use your phone and get a hypsometer app, and you just tape it up like this and sight up the side of it, and then say what's that angle, and push a button, it'll hold it, and you can look at it and find that angle. Lots of ways to find the angle, which is what you need whenever you're looking for heights of trees or that kind of thing. I don't know, did we talk about finding heights of trees here before or not? But if you're out in the woods and you have a chainsaw, which is a dangerous thing, somebody who has a chainsaw in the woods, you want to cut down a tree, and you don't want the tree to hit your house, because your house is in the woods too, I guess, in this case. How can you measure that tree? Well, you could, if you could somehow measure that angle, you could apply this trigonometry and say that you're standing here, and here's the ground, and here's this big tree, and whatever, the house is right here. It's a funny house. Must have smoke coming out of the house, chimney and smoke. Well, you could stand here and measure it. Whatever, you just want to know if you cut this tree down, is it going to hit the house? And so you look up at the tree, and you look at the top of the tree, because that's where it's going to go, and then you measure this angle. Now, here you have to adjust for this amount as well. So, but you measure this angle, and then you can step it off and see where it's at. The shortcut way, and I don't remember if we did this or not, but the shortcut way is to find a stick, and if you're in the woods, you might not find a yardstick, but you can find a stick that is exactly the length of your arm. So you do that, and then you hold that, and if I hold it straight out, you can't see the top of it, and straight up, where this leg of the triangle is compared to this leg of the triangle, and I hold this perfectly level, and this perfectly horizontal, then I'm making a 45, 45, 90 triangle. And so then I walk back or walk forward until my sight, you can't see it, but if I hold it smaller and hold it right here, I'm making this triangle here, and I walk forward or backward until the top of the tree is perfectly lined up with the top of that. Then I've just created a 45, 45, 90 triangle like this. Here's the guy, here's his arm, and here's the stick, and actually it comes from the eyeball. But you do that, and then you just make this line up to the top of the tree, and since it's 45, 45, 90, then the height of the tree will be exactly this. So then you walk back and forth until you're lined up, stop, make a mark, and then measure the distance, step it off from you to the tree, and you know the height of the tree. Or you just say, that's where the tree is going to fall, right here. It's going to fall at this point. If I did a 45, 45, 90 triangle, if I make this leg be exactly this length, and hold it perfectly straight up down, walk back and forth, and say, boom, right there's where the tree's going to happen. Where the tree's going to hit. Pretty useful, actually, if you ever consider yourself a logger. There's more tricks of the trade, I think, but that's one simple one. 45, 45, 90, and wherever you're at, that's where the tree's going to fall down. All right, enough of that. Lesson 74. We're ready at 15 minutes. Lesson 74, it's not a long lesson, but it's a little technical, perhaps. Reflection. So we're back to transforming figures. Transformation is the general term. Translation was the one where we slid them, and now specifically reflections, and that is reflecting them across a line. And we'll just look at that a little more in detail. What does it do, and how does it work, and so on. Reflection is a transformation that reflects every point on a figure, in a figure, over a given line. You have to give a line of reflection. What are you reflecting across? Excuse me. What line are you reflecting across? So after reflection, the image of the figure is congruent. It didn't change in size, but it changed in orientation. It depends what happened. It flipped this way, or it flipped down, or whatever. So a reflection is an isometry. That means, again, that an isometry just means it's the same shape and size, the image and the pre-image. It's not talking about the orientation. So the orientation changed, but nothing got bigger, nothing got smaller, and nothing else changed. So the size and shape are the same. It is an isometry. To reflect a point across a horizontal or vertical line, imagine that the line is a mirror and visualize the reflected location of the point. I was going to try to bring a mirror and set it up here, and you have a figure, and you tilt the mirror to where you could see it, and you see exactly the reflection, but I did not do that. Look at a couple of examples. Reflect ABC across the y-axis. This is example 1. We're on page 490, the bottom half of page 490. Example 1, reflecting triangle ABC across the y-axis. Find the coordinates of the vertices of the reflected image and write the transformation in mapping notation. That gets a little bit harder to do it in mapping notation, but anyway, let's see what it says. So imagine each point reflected across the mirror sitting on the y-axis. Each point will end up opposite from where it is now in quadrant 1 or 2. Remember, we didn't talk much about this. The quadrants are 1, 2, 3, 4 maybe. Yeah, this is quadrant 1. I know it's positive and positive. This is negative and positive. This is negative and negative, and this is positive and negative. Anyway, anything in this side, if you're reflecting across this line, is going to come on this side. So, first of all, the y value will not change. The up and down will not change because we're doing it exactly across a vertical line. So anything that happens at this point, it'll come across and it'll be exactly the same distance. So if this y is 7 over here, let's say this is negative 5 and 7, then it's going to be positive 5 and 7. So the y will not change going across, only the x value changes. And it's really the x just gets opposite. So everything before was negative, it was negative 7, and the x value of b was negative 2, the x value of c was negative 7. All those just become positive. So in mapping notation, this specific reflection from this line will be the translation of points x and y become negative x and y. What x was here, it is now negative. And that carries through even if you have a figure that's kind of going like this, that has some over here. You reflect it across this line and then it will end up over here, and some of this came over here. So whatever it was, it's now the opposite. If it was negative, it's now positive. If it was positive, it's now negative once you flip it over. But in this example, there isn't anything over the line. It's all over here, which is a little simpler. But that's the mapping notation for this specific one. And then reflecting across a horizontal line. Now, it gets a little more tricky when you're not at 0, like the y-axis. So example 2 is saying you're reflecting it across a line that is y equals 4. So again, we should know how to do this. Y equals 4, 1, 2, 3, 4. Here's our line of reflection. Doesn't matter what the x value is, y is always 4. So that's our mirror line, and then our thing is up here. So it's going to come down here, and however far this point was away from this line, it's going to be down here. And however far this point was away from the line, it's going to be that same distance down here, wherever it ends up. That should end up right here in this drawing. Reflect it and identify the coordinates of the vertices of the reflected image. So you just count But then the question then is, what is the mapping notation? And it gets kind of tricky. You can't just reverse it like the other one was. If it was x, then it's negative x. You can't just say if it's positive y, it's negative y, because it's not. It's not flipping across 0, it's flipping it at 4, and that comes into play. The solution has it. Again, we know that x is not going to change, so we can fill that much out. We can say the translation of points x and y become x. We know that much, because nothing changes in the x value. They're exactly the same. If this was 4 up here, it's still 4 down here. The y is a little counterintuitive. Negative y plus 8. And all I can say is that at this point that this 8 has to do with this being at 4. It's double that. And I've looked at it and kind of tried to figure them out and get them, and maybe you can, maybe you can't. But you can flip them across, and I mean you can see just by this you know where to go with it, but to actually come up with the mapping notation might be a little more difficult. The middle of the page, we already said this. Notice that when a point is reflected across a horizontal line, its x coordinate does not change. When the point is reflected across a vertical line, its y coordinate doesn't change. We talked about that. To find the reflection of a point across any line in a coordinate plane, draw a perpendicular line from the point to the line of reflection. And then the point's reflection will be equidistant from the line on both sides, which is what I said here. You draw a line perpendicular to the line of reflection, and then say that distance is what this point is going to be. That distance is what this point is going to be. And it applies for other lines. Let's say you're reflecting across this line, and you have some figure up here. We just draw perpendicular lines. You've got to draw perpendicular lines, and then straight across, that same distance is where the point's going to end up. And this same distance here, so it'll look like that, sort of, and that same distance from here to here. Example 3. Reflect quadrilateral JKLM across the line y equals x. We're at 22 minutes, probably losing your attention, but just hang on, we're almost done. Example 3, reflecting across the lines. Reflect quadrilateral JKLM across the line y equals x. Well, I don't know if we talked about these types of lines, y equals x. We've talked about, horizontal lines and vertical lines. I don't have my coordinate graph paper up here anymore, but if this is 0 and 0, the line y equals x is for any value y, the x is the same for any x, y is the same. So it's like 1 and 1, 2 and 2, 3 and 3. It's a 45-degree angle going up. So that's y equals x. This line is y equals x. I hope that makes sense. And then you're supposed to reflect it. And you do it on graph paper. You're going to need graph paper for these examples. You do it on graph paper and list the coordinates. And then it doesn't say to do a transformation mapping necessarily, but sometimes it may. For this one, since the line is y equals x, that's kind of the answer as to what's going to happen. So the transformation mapping notation is going to be the transformation of x and y becomes something. Well, we just said that y equals x, so what was y will now be x over here, and then what was x will be y. That's how it works. But that is exactly the mapping notation of flipping it across y equals x. Whatever value x was on the old one, that's going to be your new y value, and your new y and your old y will be your new x. It swaps. We'll skip the last one. All right, that's it. So I did not give you homework for 73 at the end of that video, or when we're done there, but we will do it now because it's all one video, I guess. Homework for lesson 73 and lesson 74. This is due Monday, please. So work on it today and tomorrow if you care to, but have it ready Monday morning. Lesson 73, the homework is 1, 3, 7, 11, 17, 20, 23, and 29. For lesson 74, homework is 2, 11, 12, 13, 14, 19, 19, 27, and 28, and I did skip one in there. I skipped one that was right in here for your benefit. All right, that's the homework for 73 and 74. Maybe I should pass out evaluation sheets. I know some other teachers were doing that. It looks like we may be doing this a little longer. I was hoping we could finish out this class together because there's some interesting stuff out ahead. I've been saying that and it's still true. But we may have to do this the rest of the time. So what I'm suggesting is if you have suggestions, improvements, things that I should do or shouldn't do, then text them to me. And if you want to text it privately, you can, or if you want to slip an anonymous note somehow to me, that's fine too if you don't want to say your name. But I'm open to your suggestions. What can we do to improve this experience? Thanks.